and welcome to the Amory SDS presentation. We were advised by Dr. Rob Kelvey and Dr. Jillian Morrison. I'm Brendan.
Hi, I'm Sky.
Hi, I'm Ben.
Hi, I'm Karen.
Our project was working for the STEM Success Initiative, or the SSI. The STEM Success Initiative is a program that tries to help underrepresented and all students achieve a quality of teaching and learning in STEM fields. We helped them through looking at retention and persistence, which within STEM fields, which is looking at how students start and end their STEM career at Worcester. Retention is a student starting taking a STEM class their freshman year, and then continuing through and becoming a STEM major. We don't care about what STEM class they took, just so they took a STEM class earlier in their career and they stuck around. That is a retained student. Persistence is a smaller version of that, which is a student staying from one class to the next class in the track. So a student that takes Calc 111 and then takes Calc 112 persisted from Calc 111 to Calc 112. And we use that and a bunch of other metrics to determine how the SSI should best use their resources, specifically looking at underrepresented or UR students, where an underrepresented student is a non-white, non-Asian student, and that's an inclusive definition. And then we had an overall holistic view of looking at how can the SSI be most helpful and what are things that they're doing that are being used.
So this first graph just kind of gives an overview of kind of the retention problem that we were looking at. So this graph is based on students who took a STEM class in their first year after indicating that they were interested in majoring in STEM on their Worcester application. And so we kind of used this intended major as a metric to figure out which students were interested in STEM. And so we can see from the graph that proportionally more underrepresented students are not retained of those students who said that they were interested in STEM. And so this is kind of just putting a visual to the problem that the SSI wants to solve of helping more underrepresented students so that these percentages are more equal.
So in analyzing students' persistence in STEM, we have two versions of analysis, one including all of the students who have taken at least one course in a major, and the other analysis only focus on students who show initial interest in STEM, in certain STEM areas. So those taking STEM classes merely as a general education requirement are removed from the second analysis. Here is the flowchart of persistence for math courses, featuring only students who show initial interest in math and computer science based on the courses that they have taken. So we can see that the persistence rate after Math 112 is increases out compared to after Math 111. 84.3% of those taking Math 111 persist to Math 112, while 90.82% of those taking Math 112 persisting to taking either 1, 2, or 3 courses among Math 211, 212, and 215. We can see that after Math 112, most students who persist take all 3 of the courses. Math 1 to 11, 212, and 215. We also look at the relationship between of persistence with course grade and math placement score, and we find that those who persist tend to have higher course grade. The difference in math placement score between persisting and not persisting students is not clear. When we did the first version of this flowchart, which includes all students who have taken at least one math course, the persistence rate is much lower, which is about like 40 to 50%.
A majority of our work for the SSI was done on modeling, and this section is going to be looking at each of the types of models that we did. One of the first types of model that we worked on was the clustering model. The idea behind a clustering model is that it allows us to take each student and based on attributes, put them into clusters or buckets. And then this, looking at those clusters, we can make sort of predictions, but this is not designed to be a predictive model. It's a way of analyzing the data in a different perspective by looking at how we sort the groups. The idea is that each dot is a student, and the group that they fall into is based on the data that we feed into the model. Our data is best fit by two clusters, and we can see general trends across them, which is that in group one, we have students that do better in grade, do better math placement score, take more classes. There's a huge difference in grade, with an average student in cluster two getting a C, and an average student in cluster one getting a B plus or so. And this is one of the ways we were able to look at students.
So next we looked at linear and logistic regression to predict the chances of retention using logistic regression, and to predict mean grade using linear regression. And so for predicting retention, we found that the highest effect was number of classes and mean grade. And so both of those have a positive relationship. So the more classes a student takes, they have an increased chance of retention, and the higher their mean grade, their chances of retention increase. And so this is why we then wanted to look at mean grade, because we wanted to help the SSI understand how they can assist students in raising their mean grade and therefore increasing their chances of retention. So when looking at mean grade, we found that the most effective predictors were gender and underrepresented status. And we can see the effects of those in the chart on the right. And so for predicting retention, we found that this model has an accuracy of 82.1%. And so the SSI can use this model and the model for mean grade in future years to help identify students who have certain characteristics, who may or may not struggle, and who may or may not be retained.
Another approach we try to predict retention is random forest model. In order to construct the model, we provide the model with a list of predictive variables, which are listed as on the right, and we ask the model to use 2,000 of trees and to compare two variables at each node. In the result, unfortunately we see that the UR and first generation and gender are not very important, so it's not very effective in predicting retentions. So we decided to drop it, and we got an estimate of error rate at 16.76%, and below in the table we have a confusion matrix. So as Sky mentioned in her model, in this random forest tree model, the number of STEM classes a student took in their first year is also the most important variables. And so this also indicates that the first year data is very crucial to predicting retention, and SSI can use this model to predict retention of a student, of a STEM student.
So finally, in predicting persistence, we use the naive Bayes classifier. This classifier is based on the theorem, which it tries to predict whether a student taking 100 level courses within the major will proceed to at least 100 level course in that same major. Here are some of the findings from this classifier. First, intended majors is a common predictor for all majors. So for example, before going to college, if a student indicates that they are interested in majoring in biology, they will be more likely to persist in biology. Secondly, this classifier works best with a bigger major like math, biology, and chemistry. This is also for the other smaller departments like computer science, earth sciences, physics, biochemistry, and neuroscience. The sample size are really small, so further additional data will need to better finalize the model. Another interesting finding that we found is that even though some of the identities that come with the students, such as gender, first generation, or underrepresented status, are not influential factors in predicting retentions, as Sky and Ariel mentioned. However, we can see that gender, first generation, or underrepresented status are selected as predictors for some of these majors. For example, first generation as predictors for positions in biology, chemistry, and neuroscience. Here is a more detailed example of how we use the model to predict persistent choice of two random students in the class of 2021, 22, and 23 who have taken at least one 100 level biology class. With the given information, the classifier predicts that both of the students will not persist to 200 level classes. So here is some of the final conclusions from our models. We will leave it here for questions when you have questions for reference. And now we're going to talk shortly about our takeaways from our Emory experience. For me, one of my takeaways from Emory is I should be more self-confident when solving problems. A lot of the times I was afraid that I would not be able to work on such a complicated project. But after a thorough process of thinking individually and also especially discussing it with my teammates and our advisors, we managed to come to the findings presented earlier.
Yeah, for me, I think that gaining the experience of working on a team remotely was very valuable because I learned a lot of different problem-solving skills and different communication skills that came along with working remotely on a team versus being in person with my team members.
I had never worked with statistical software like R that we used, and so I learned a lot of how to think and interact with data and statistical software that I hadn't known before.
For me, the major takeaway I have is the experience to cooperate with people and the gaining of the knowledge of some data science and also the gaining of giving presentations. Last, we want to say thank you to the Hamburger Fund, the SSI, and Emory for the opportunity to work on this project. Please let us know if there is any questions.